has worked for 6 years in the field of cryptography for the Uni Karlsruhe. Oaths.
Okay, so thanks for the introduction and welcome to my talk. As our herald just said, I've been working in the area of cryptography for the better part of the last 6 years, and I noticed that many people today have kind of a mental image of what cryptography is and what encryption is, but sometimes this mental image does not really coincide with what is actually going on. So I wanted to give an introductory talk to cryptography that is available to a broad audience, so to an audience that does not have any prior exposure to cryptography, and maybe even to an audience that does not have a background in maths or computer science. So, as I said before, this talk is specifically aimed at a non-technical audience, even though at 36C3 we probably have a fairly technical audience, and this is a foundations talk. So I will not be speaking about fancy research or cutting-edge results. I will be talking about the plain basics. Okay, so apart from working in cryptography, I enjoy doing applied cryptography, number theory, and pwning, so exploiting all kinds of memory corruption bugs in programs. Okay, this is a picture of my parents' cats, just because every talk should have pictures of cats in them. And this is, thanks. So this is my checklist for this talk. The first item, I think we already did that. And so for the remainder of the talk, I want to explain what encryption is, what it does and what it does not do. I want to explain authentication, which fixes a problem that encryption does not solve. I want to explain certificates because they help a lot with both encryption and authentication. And in the end, I want to explain a little how the things that I'm going to introduce work together and can be combined to build more useful things. Okay, so let's start with the first point here. I would like to explain encryption. So encryption is basically a solution to a problem, so let's talk about the problem before we get to the solution. The problem here is, or one of the classical problems, is that two parties want to communicate, so we cryptographers commonly call them Alice and Bob, and Alice wants to send a message to Bob. So in this case, it's just a very stupid message, just a simple hello, but cryptography has been used in diplomacy and military for hundreds of years, so imagine that this message is something more critical. And the problem we want to solve is that there might be an eavesdropper who is wanting to listen in on the connection and read the message, read the content that is being sent from Alice to Bob. And what some people think how cryptography works is something like the following, which is kind of close to the real thing, but not really, is that Alice applies some kind of encryption procedure to her plaintext message to produce some random unintelligible gibberish, which we call the ciphertext. And then Alice sends the ciphertext to Bob, and Bob has the decryption procedure, knows how to decrypt, so to invert the encryption procedure and recover the plaintext message. And now, a point that some people get wrong is some people think that the knowledge how to decrypt is actually secret, but that is not true today. So in 1883, a person named August Kerckhoffs formulated a couple of principles that ciphers used for military applications should adhere to. And one of these requirements became well known as Kirchhoff's principle, and it reads, a cipher should not require secrecy, and it should not be a problem if the cipher falls into enemy hands. So rephrasing this a little, the cipher that you are using should be secure enough that you can even tell your enemy or the attacker how the encryption process is working and how the decryption process is working without harming the security of the encryption. Or to rephrase this yet another time, if the cipher you are using is so insecure that you cannot tell anyone how it works, then maybe you shouldn't be using it in the first place. So let's get back to this image. So now if the attacker knows how to decrypt the message, then obviously this very simple scheme does not yield anything useful. And so what people did is people introduced a key to this image. So now the encryption procedure and the decryption procedure use a key, which goes into the computation that is going on. So Alice does some kind of computation based on the message and the key to produce the ciphertext, and Bob, who has the same key, can invert this encryption operation and recover the plaintext. However, as long as the key is only known to Alice and Bob, but not to the attacker cannot use the decryption procedure. So one general word here, I will not go into the details of how these boxes operate. So within these boxes which represent computations, there is some math or computer science going on, and I would like to not explain how these things operate internally in order to keep this talk available to a broad audience. Okay, so a problem that we have here is that Alice and Bob have to agree on the key in advance. So Alice cannot simply send over the key to Bob, because if she did, then the attacker who is eavesdropping on the connection learns the key as well as the message, and then the attacker could just decrypt the same as Bob. Okay, so this does not work. This is a terrible attempt. So for quite some years, actually until the 70s and 80s of the last century, people were only using this scheme, and this is what we call symmetric encryption, because we could just flip the image around and Bob could be sending a message to Alice instead, because encryption and decryption uses the same key. And if there is symmetric encryption, you can guess there is something else which is called asymmetric encryption, and there is, for asymmetric encryption, there is a pair of keys. One of them is used for encryption and one of them is used for decryption. And now if we have an asymmetric encryption scheme, we can do something like the following. So Bob generates a pair of these keys, one for encryption and one for decryption, and he keeps the decryption key to himself. This is why the decryption key is called the secret key. However, Bob can publish the encryption key for everyone to see. So for example, it could be put in a kind of public registry like a phone book or whatever. And now Bob can send his public key to Alice, and an eavesdropper who is listening in on the connection will learn the public key, but that's not a problem because the key is public anyway. And now, after we have done this, Alice can use Bob's encryption key to encrypt her message and send that over to Bob. And now Bob can decrypt the message with his secret decryption key. However, the eavesdropper here cannot simply decrypt the message because even though the eavesdropper has the encryption key, it does not have the decryption key, and thus the eavesdropper cannot decrypt. Okay. However, this solution is still kind of risky. There is still a problem with this, and it is we still have to make sure the keys are distributed in advance. Okay, so if we used this simple scheme where Bob is sending his public key to Alice, then there is a problem if the attacker is not simply passively eavesdropping on the connection, but is willing to actively interfere with the connection. So for example, the eavesdropper might intercept the public key that Bob is sending to Alice and replace it with his or her own public key. And then Alice would think that the key she received belongs to Bob and use this key to encrypt her message to Bob, and then suddenly the attacker can read the message again. So at this point, let's summarize about encryption. So encryption conceals the content of data. And this is pretty much what it does, and pretty much the only thing that it does. In particular, it does not conceal the fact that there is communication going on. So an eavesdropper who is listening in on the connection obviously can see Alice sending a message to Bob, and thus the eavesdropper knows there is communication going on between Alice and Bob. And this alone could be quite dangerous for Alice and Bob. So imagine if Alice was working for an intelligence agency and Bob was a journalist, and the attacker sees Alice sending lots of documents to Bob, then this might be a strong indication that Alice is a whistleblower and Alice could be put into jail. So something more that is not concealed by encryption is the amount of data that is being exchanged. So if Alice is sending just a very short message to Bob, then the eavesdropper can guess that the message that is being transferred is not a 20 gigabytes file or something. So all this kind of metadata is something that encryption does not conceal. And there is a couple of more problems with encryption. One of them is that the attacker might change the message. Protecting from changes to the message is not the job of encryption. Another problem is that keys must be exchanged in advance, which I already talked about. And there's more problems. So for example, an attacker might simply record a message when it is sent and later just replay this message to Bob. Or an attacker might go ahead and block a message altogether, so intercept the message and throw it into the trash to make sure it never arrives at Bob's site. Okay, and the first problem here, an attacker might change the message, will actually leads me to the second part of my talk, which is authentication. So on my talk checklist, let's mark encryption as done. Okay, so now what is authentication? Authentication enables the detection of changes to data. It does not prevent changes from happening. It only enables the recipient to detect the changes after they have happened. Okay, so for example, or one example where something like authentication was needed is when Bob was sending his public key to Alice, but this is by far not the only scenario where authentication is needed. So imagine if Alice is running a charitable organization. So for example, she's saving refugees from drowning in the Mediterranean Sea, and Bob wants to donate to Alice to help her do that. Then Alice has to send her bank account number to Bob so that Bob can make the donation. And notice that In this scenario, the message that Alice is sending to Bob, her bank account number, is nothing that is secret. It does not have to be encrypted because this information is public knowledge. However, we do want to make sure that the message that arrives at Bob is indeed the correct bank account number. So to prevent something like this from happening, where a criminal might intercept the message and replace the bank account number, so Bob would send his money to the criminal's bank account instead of Alice's. And one way to realize authentication is, again, by having a pair of keys. One of them is used for authentication, and one of them is used for verification, so checking if a message has been changed or not. And the authentication key must be kept secret, thus it is called the secret key, whereas the verification key can be made public, and it is called the public key. And now if you have a setup like this, then Alice can go ahead and take the message that she wants to send to Bob and apply some computation to it together with the secret key, the authentication key, to produce something that we call a signature or a digital signature. And then Alice sends this signature over to Bob along with her bank account number. And Bob will take the signature that he receives and the bank account number he receives and apply some kind of computation to them. And this computation will determine if the bank account number has been changed or is in fact original. So if the attacker changes the bank account number, then Bob will be able to detect this change by checking the signature. And this holds even if the attacker does not only change the bank account number, but also the signature. Okay, so these things are designed in a way which hopefully makes it impossible for any attacker to come up with a valid signature for anything else than the original message. Okay. So the only thing that Bob will, the only way that Bob will accept the signature is if the attacker does not, in fact, change the bank account number. And in this case, it is safe for Bob to transfer the money. Okay. But here, okay, so here is a different solution to this problem, and it's actually pretty much the same, except that now we have just a single key which is used for both authentication and verification. And in this case, things simply have a different name. They work in exactly the same way, except that the signature is called a message authentication code, or MAC for short. Okay, but in both of these scenarios, whether we have two distinct keys or just one key, we still have the problem of key distribution. Okay, so imagine if in the scenario with two keys, Alice was sending her public key to Bob, then we would have the same attack as before, namely the attacker could just go ahead and change the key that Alice is sending to Bob and exchange it for his own key. And so if the attacker is sending his own public key, his own verification key to Bob, then obviously the attacker can create a valid signature for his forged bank account number, and Bob would accept this. Okay, so again we have this problem of key distribution, which is that the verification key must be known to Bob in advance. Okay, and this leads me to my next the next section of my talk. So let's mark authentication as done and go on with certificates.